webinar is being recorded. So of course, we'll publish the recording and we'll also publish the slides. So you can find all the slides and the recording on ENTSO-E's website, on the TYNDP website, within 1 or 2 days. So still this week. Now, while still a few more people connect, I will quickly go through the agenda. So we'll start with an introduction by Patricia Labra, who is the convener of the TYNDP steering group, just to set the scene on what do we mean by system needs. Then we'll move to a first part and a new component of the TYNDP assessment of system needs, which is the offshore network development plans. We'll take questions, of course, then we'll move on to a part of the TYNDP that you may already know, which is the system needs study. It's been, I think, released since 2018, every 2 years. And we'll conclude with another study, also part of the overall system needs galaxy, which is the inertia project. How can you participate today? So we have set up a Slido, so you can join at slido.com and enter the code that you see here, so 2340515, or use the QR code here on the right. We will show this QR code again during the webinar, so there is no rush. So we will use Slido to have 2 polls with you, and we will also use it for questions. So please do not send questions in the Teams chat. I think it's disabled anyway. Please put all your questions on Slido and state your name and organization if possible. So without waiting anymore, I will give the floor to Patricia for the introduction.
Hi, good morning. Yeah. Thank you, Leah. Well, my name is Patricia Labra, as Leah mentioned. I'm the head of network planning at Red Eléctrica and also convener of the TYNDP at ENTSO-E. Good morning, everyone, and welcome to this webinar. First, I want to thank you very much for your interest on joining today. We have a lot of people already joined, around 100 persons, and there are more people registered, so there probably will go on joining. Well, this for ENTSO-E, it's very important to build our products. Yeah. Sorry, wait a minute. I think that we can see the slides, right? Yeah. Okay, great. So I was saying that well, for ENTSO-E, it's very important to build our products together with the stakeholders, and that's the reason to have this session and discussion today. And gather your view as relevant experts of the energy sector. The TYNDP is one of the most relevant products of ENTSO-E and the System Development Committee, as it gives a global vision of the future of the European transmission network. Today's presentation will allow to give you an overview on how the system needs exercise is intended to evolve in this TYNDP 2024. We will enter probably in quite a lot of technical aspects, but they are relevant to understand the approach and the global optimization that pursued with this exercise. So don't be shy. Please interact, clarify your doubts, and give your feedback during the session. So let's start with an overview of the TYNDP process and the timing for the current process ongoing. Some of you will probably know this slide, but for those that are new in the process, I think it's quite relevant to understand how it looks like and where also the system needs is considered. So every plan, every TYNDP starts with the scenarios definition. They are a set of possible futures which are used to assess the future needs and to assess infrastructure projects. The 2024 scenarios are in progress since the beginning of this year in the new context of the framework guidelines set by ACER after the updated TENE regulation last year, and they will be finalized in the first quarter of 2024. After defining the scenarios, we identify if the grid ensured for a certain time horizon, we usually call the starting grid, is adequate. That is it enough to fulfill the European objectives? If not, the weak points that we detect in the system are identified, and all the results are included in the system needs report that is part of the TYNDP package. It's one of the main bricks of the TYNDP package, in fact. As a relevant new in this TYNDP 2024 release, for the first time, we have a dedicated analysis for the offshore grid in the framework of the first edition of the offshore network development plans that will be released in January next year. And how the onshore and offshore interrelates. Yeah, this step that has started beginning this year, mainly with the offshore part, will end in the second quarter of 2024. The third step is the collection of infrastructure projects that could solve those needs. We ask project promoters to propose transmission and storage projects based on the previous needs exercise. Probably you are aware that we had the call for projects to the 2020 to the TYNDP 2024 between September and mid-October, so quite recent. And for that call, the guide for project promoters was the identification of system needs report published in 2022. Now we are checking the data that we have received. Yeah, the applicant projects that are compliant with the ENTSO-E guidelines for project inclusion with the technical and administrative criteria set on those guidelines are included in the TYNDP project portfolio, and therefore they are assessed following our cost and benefits assessment. And this assessment that is really intensive in simulations and data analysis will take place during the year 2024. These are the fourth step of the TYNDP, responsibility of ENTSO-E, which fit into the PCI and PMI processes led by the European Commission. As this system needs exercise and the individual CBA assessment are used in this official process. And as you probably know, getting this PCI, PMI level allows to obtain a set of advantages related to political support, faster permitting, financing, and sometimes some grants also. Okay, so I think that we reach here to the first question of our polling survey. Yeah, if you hadn't joined the Slido yet, you have here the QR code and also the number, yeah, to join. We want to know what should be, in your view, the primary objective when assessing the future system needs. You can rank what you consider of higher priority between the options that you have here, which are, well, determine the infrastructure required so that manufacturers and supply chains are ready to deliver that on time. Yeah, also it can be identified what are the inefficiencies that should be addressed to lower electricity cost. Yeah, with that focus on affordable electricity cost. Also identify where security of supply could be improved, or make sure that our power system is compatible with the energy transition targets. So I see that we have already 11, 12 answers, but we have around 120 people in the call. So let's see how it evolves. And by now, the preference or the main objectives is ensure that the grid is compatible with energy transition targets. That is true. That is quite in line with many of the discussions and studies that are being published by different entities. Also, the International Energy Agency have asked to put the grids, in the front row of the discussion of the energy transition, due to its relevant as facilitators or enablers of the energy transition. The second option by now is to give a wide view for manufacturers and the supply chains to be ready, because well, it's true that that the increase of investments that are supposed to be required in the next year is quite high, and possibly also the supply chains have to be accommodated to that new demand. By now, the third option is the security of supply issue, that it's always relevant, at least for us as system operators. It's very relevant, and also in a continent as Europe, where the security of supply, we assume the electricity as a primary good. So we are used to high security of supply levels, and we want to maintain them. And the affordability of the energy by now is the fourth options. Also, it's there. So it still moves a little, but the order is maintained the same. Thank you very much. I think that by now is stable. Objectives, supply chain, security of supply, and affordability of the energy. Okay, so I think that we can go on. Thank you very much. So let's go on and give also our view here. What are we talking about when we talk about power system needs? They try to answer the question of what should the electricity grid look like in 2030 and 2040 to ensure continuous access to electricity, to create maximum value for Europeans, and to deliver on the climate agenda. Therefore, the objective of the power system needs exercise is to investigate where improving the electricity flow through Europe would be the most efficient, the most cost efficient from a pan-European perspective. And this exercise intends to be an optimal portfolio global optimization. It shows borders and areas where new solutions are needed to reach decarbonization targets and keep the security under control. You can see at the ENTSO-E website what's the results of the power system needs exercise in the previous process. And today we will see how we intend to improve it, and what's the approach for the assessment. Let's see also in the next slide that although we have different studies that serve to the same global purpose, that is the scenarios, the offshore network development plans, the ONDP, and the system needs studies. they are related to each other, but they aim to answer different questions. On one side, the scenario that are developed together with ENTSO-E try to answer what the European energy system would look like in the proposed storylines. We have an expansion model especially applied to the storylines that have a top-down approach, such as the distributed energy or the global ambition in the long term, 2040 and 2050, where the optimizer can invest either in generation, infrastructure, and also demand-side response and other flexibility measures. But the offshore hybrid projects were so far not part of this optimization in the scenarios. Then we have the first release of the ONDPs, in which we have been working this year. And they want to give a hint on what does it take to integrate the offshore European objectives, that is the 360 gigas in 2040 and 480 gigas in 2050. As scenarios of the TYNDP 2024 are not closed yet, the 2022 distributed energy scenario has been used as a relevant one in the ongoing PCI process, as the most valid one in the current energy context. And here in this exercise, the optimizers is only allowed to invest in offshore infrastructure. So we isolate the offshore challenge to focus on the details of its analysis, and all the other parameters remain fixed to avoid make the optimization problem too much complex. But for sure, we cannot give a solution to the offshore grid without taking into account the interaction with the onshore. Then we came to the system needs exercise that, as I said, tries to provide the most cost-efficient solution to the electricity system and tackle here both the onshore and offshore. Here the analysis is made on the new national trends scenario, which can be considered as the central one for 2030 and 2040 as the most representative for the TYNDP 2024. As it is the bottom-up scenario in line with national views on how each country will contribute to the updated European targets. And for 2050, the distributed energy scenario will be used, as there is no bottom-up scenario for such a long term with national inputs. Here, the optimizer can invest in transmission, in storage, and in offshore hybrid candidates, considering the output of the offshore network development plans with the corridors that we have there. So every study gives us relevant information with different focus to try to define and build altogether the correct grid at the correct time to serve to the energy transition and the decarbonization of the European economy. And in the next slide, here, I mentioned at the beginning that the importance of co-create our future system with you. So how can you provide your input on the system needs exercise? On one hand, the offshore network development plans, they will be published in January 2024. And we will organize specific events to explain the result of this first publication and a consultation that will allow us to improve the 2026 process, where the ONDP will be fully integrated in the TYNDP usual timeline. But this time it deserves a particular focus and an individual consultation process there. On the other hand, on the system needs study, you can provide your input today in the webinar, and until the end of November on the methodology. We are also open to discuss bilaterally in case of interest. You can contribute to your particular input on the inertia study in a dedicated webinar that will take place in November. Today we will see a small part of it, but we will organize something with more detail in November. And you can for sure give your view on the system needs exercise once the document of the system needs studies is published. We expect to publish it in summer 2024, and it will have a dedicated public consultation. So with that, with this introduction, I give the floor to Angie and Francesco, who have been leading the offshore topics at ENTSO-E for a long time. So
Okay.
thanks.
Thank you, Patricia. So now I take the screen. Okay, now you should see the screen. Welcome to this part of the TYNDP event today. So now we're going to explain a bit how we do the offshore network development plans. So my name, as Patricia said, is Antje Orts. I work for Energinet, and I'm leading the work on the offshore development plans across all sea basins. And I have big help in Francesco, whom you also see at the screen, showing his face. Yes, now let's go. What is the offshore network development plan? So it's a new task, a new part of the TYNDP that deals with the offshore part. So we have received the mandate to investigate this in the TEN-E regulation last summer. And so we had to develop a new part of the TYNDP and are quite good shape now. So the main answers you receive from the offshore network development plan are indicated here. So you will receive answers to where is offshore RES capacity expected in the different sea basins, how much is where, and how is it interlinked? Is it interlinked with each other or not? So then we look into the configurations for connecting different clusters, and also look at which space is actually available. So because the sea is used by different parties, different users, and we have to take care that the coexistence is possible. So there are plans from the European Commission and from the member states, which we consider, and so this is then part of the ONDP. We have to consider, according to the regulation, the interconnectors, which is mainly part of the classic identification of system needs. Then we look into radial connections. This is new. Then we look into hybrid projects, and what this is on the next slide. And reinforcement and also hydrogen infrastructure is a task which will be improved along the next TYNDPs. So we start with the capacities received from the member states, because the member states have the task to deliver the capacities, the non-binding capacities that they expect for 3 time horizons, 2030, 2040, and 2050. And this is our input and the base for the investigations on the infrastructure. What we do is translating the member states' capacities into infrastructure needs. And we come back with high-level information, how this looks like. This is then part of input related to the cost-benefit, cost-sharing discussion, which then is guided by the Commission with their methodology, which they will deliver in next summer. And then we again have to apply this methodology on the product you see developed today. So hybrid project, offshore hybrid project, what is it? It is a combination of 2 functionalities. So it's the functionality of connecting offshore RES to the onshore system and of interconnecting countries or market zones. So this is something new. And it's important to mention that for us, generation assets are out of scope. They are not part of what we look at. So when we look at cost and benefits, that's tackled by the developers. However, it's important that we have the full overview when wanting to build, so that we know from the developers what do they plan where by when, so that we are on time with our infrastructure. But for this exercise of the offshore network development plan, this is, and all the other position papers we developed, this is out of scope. When we talk about dual purpose, it's what I just mentioned, and sometimes you even talk about multi-purpose. This is when energy sectors are crossed. So it might be that even flexibility measures, or for example, electrolyzers are included on offshore energy hubs. So then we cross energy sectors, and then we call this multi-purpose.
Good morning, everyone. So how the methodology has been set up to investigate the needs in terms of offshore infrastructure connecting the REST targets. So we divided the work in 3 main steps. The first step covered the data gathering. So starting from the member state targets, we got information at national level on the granular distribution of the capacities in terms of PCD zones, in terms of clustering of type of connection configuration. We defined the candidate links in order to expand the transmission infrastructure connecting REST to the onshore system. And we adapted the TYNDP 2022 models that had been used to develop the expansion loop of the ONDP. Why we use the TYNDP 2022 models is basically they, as of today, the TYNDP 2024 are still under development. And so since we needed to start the ONDP already at the beginning of the year, that was basically what was available, what is now publicly available to be worked with. We use the distributed energy model, since in terms of capacity was the most similar to the one that through the system we characterizing a system with the REST targets included. The second step was the modeling itself, expanding the 2040 and 2050 time horizon. We have not expanded 2030 because in 7 years the configuration of the system is, let's say, is assumed to be well known. We have a certain amount of known projects in terms of, let's say, portfolio, in terms of what is now in the pipeline. So we decided to concentrate the modeling investigation on the 2040 and 2050 horizons. Of course, we run an internal feedback loop with national experts to adapt the model and to adapt the, let's say, the model with the first results of the modeling runs, so that then we could arrive at step 3 with post-processing and drafting of the CBASE reports themselves. For the 2030, of course, we drafted the report based on the data gathered under step 1, describing the expected system in the different TYNDP corridors and basins, and post-process the results for 2040 and 2050 in order to individuate the transmission corridors that show the most potential in terms of development of hybrid infrastructure. And then, of course, the drafting of CBASE reports themselves and all the accompanying documents composing the ONDP package.
So here you can see, once again, a visualization of step 2 and 3 as just described by Francesco. So we start to the left. We use a starting grid. So we use the model of the TYNDP 22 as this was available and time is short. So this is composed of the distributed energy scenario, and we did the modeling for 2040 and 50. And when we did the modeling for 40, we started, of course, with the situation assumed in 2030, and then we took the results from 40 as input for the 2050 simulations. So this is then the starting grid. The optimizer then had received a number of candidates. So expansion candidates, this is from each nearly each of one offshore node to another, so that the entire possibilities have been there for the optimizer to select based on minimization of TOTEX, CAPEX and OPEX. So so all the possibilities were there. Then in a next step from 2 to 3, the optimizer did his work and found then the links that are beneficial, economically efficient for the system. So they are indicated in green on as example on the third map. And then we gave this to the regions, because now local expertise is very important. And the regions then applied their local engineering expertise and selected the links that are plausible. So, for example, when they discovered a very small link, a 50 megawatt link between two nodes, nobody would build an HVDC connection of that size. This was then discarded, or it was aggregated with another link in the same direction or between the same countries in vicinity. And so this was then what the regions did. They delivered their results back to the central process, where we centrally ran for all sea basins at the same time another loop without expansion, and so that we have hourly results for production and generation for the European system.
So in the ONDP, an important part of the analysis on the offshore infrastructure has been the integration of MSP, the Maritime Spatial Planning information coming from the member states. For the one of you who don't know, the MSP has been a deliverable developed by the different member states to organize and plan from a spatial perspective the utilization of maritime space in order to coordinate different sectors. And of course, energy is part of it. The ONDP model have been, let's say, the results have been adjusted in order to include the information. Why is that? Because of course the model itself use a straight line length, let's say bird's view. But of course, in reality, the route needs to avoid certain areas. For example, nature conservation, exclusion areas due to other sectors like military, for example, or already existing infrastructure. So we had to adjust when estimating the route to be covered with electrical transmission infrastructure. We had to adjust the final amount with a certain, applying a 15% to take into account all the possible deviation. And in general, of course, the routes, the corridors have been assessed to check that there are, let's say, that we are not crossing any huge let's say, blocking point represented by exclusive use areas. This has been first, let's say, it's something that's been done for the first time in a TYNDP exercise. We have to say we have received some quite good information, especially in the North Sea, waters, where a lot of information and coordinated one was available. And so, yeah, it definitely delivered quite a good addition to the analysis for the electrical infrastructure.
So now question, is there anything what we not have done or what is imperfect, maybe, or children's disease? Because again, remember, it's the first time we do this. We use a bit different methodology compared to the classic TYNDP. You will see this when you follow the webinar a bit further. And so what should you have in mind when one day reading the results? So we are proud that we reached this target. So we used the member states non-binding goals provided in January, and we are based, the results are based on close TSO collaboration with a lot of local expertise. So have in mind that we used the TYNDP 22 scenario model. So everything was fixed and data collection was coming from even earlier, so from kind of 2020, 2021. And we mounted then the new member states offshore targets on this older model. And so we also increased arbitrarily across Europe the demand by 8%, for example, to reflect the electrification better, because it was not that extensive in the TYNDP 22, but we can see it in 2024. There's a lot more electrification represented by the scenario data. So to come closer to this, we increased the demand by 8%. We did not do an economic evaluation or adjustment of the overall production portfolio, so everything was kept stable, because the question, as indicated in the beginning of this webinar, the question is different from the classic TYNDP. So we ask the optimizer, how can we implement the offshore RES coming from the member states? We don't ask what is the optimal system, but how can we implement it? And so the optimizer, therefore, was only allowed to invest in offshore infrastructure. All the rest was kept stable. And so the implications on the onshore system are then part of the identification of system needs exercise, which starts now. And so we use then the results that will be published in January, put it into the TYNDP 24 model ongoing now, and assess then both the offshore results together with the classic exercise for the TYNDP 24, and then we will see the implications on the onshore systems. Yeah.
So what are the next steps? As already mentioned previously, the ONDP will be published in January 2024. The new TANIA regulation includes a legal deadline of 24th of January. Of course, there will be opportunities to engage via consultation and dedicated workshops in January, February 2024 in order to start preparing already for the 2026 edition of the TYNDP and the ONDP itself. So towards the work that lies ahead of us, we will definitely, what we aim at is getting the methodology that we used in this first edition forward in terms of inclusion, even more holistic approach in terms of parallel development of the two systems, and complete the integration with the existing products, especially when it comes to sector integration, with further collaboration with ENTSO-E to investigate expansion of the hydrogen infrastructure. Of course, we will take any feedback coming in order to increase stakeholder engagement, to make the ONDP and the TYNDP in general a better product.
And what can you expect from the ONDP in January? So as the TYNDP, also our offshore network development plan is not just one report, it's a stack of reports. So we have 5 sea basin reports as requested in the regulation. So for each sea basin, which is defined quite clearly in the regulation, for each sea basin, one report. Then we will have one pan-European report summarizing these sea basin results and also giving some high-level information. We will publish the methodology, how we have done it. We will, as usual, also have a report on stakeholder engagement. And the best is then the interactive online visualization tool. So where you can select whatever you wish to see and can assess whatever is important for you. So, and the contents is, of course, as indicated in the beginning, how many offshore RES is where, how could the offshore infrastructure look like based on different assumptions on technology development, for example, on cost development, and this is combined into configurations, and you will see variants of possible infrastructure, high level, of course, high level corridors, because we don't work on projects, we work on corridors as we do in general with the identification of system needs. And of course, you will also see which assumptions we have done, for example, on the cost. That's always a question, and the situation is not easy. But giving this information, this should then help on European level to accelerate the offshore expansion, as then the information is on the table, how much infrastructure assets are needed in which situation based on the high-level targets from the member states. And having this information is then important for industry to prepare. Maybe we need more cable factories or whatever asset factories in Europe. You will see in January.
Thank you very much,
Yeah,
Angie and Francesco. So now we move to a Q&A. I've seen there are already some questions on Slido. So Emil, if you could please put the questions on the screen. So the Slido URL and code are the same as we've shown previously, but I think you will see them on screen in a few seconds.
Yeah. So you should be able to see it now.
So starting with the questions we already have, I will read the first one out loud. For the identification of offshore interconnection candidates, what are your constraints and assumptions in terms of technology, size, capacity, predefined corridors? Do you use a kind of heuristic approach? Who wants to take that one? Francesco?
If you want, yeah, absolutely. So to expand the interconnection between the different, let's say, clusters of renewable, we assume the use of HVDC technology in, let's say, as a standard transmission technology. We explored different possibilities in terms of development of HVDC technology based on availability or not, for example, of DC breakers. To explore, let's say, of course, the different configurations and the economic consequences of having different configurations. We have not put for this edition, let's say, AC and DC in, let's say, direct competition for short distances. But in general, what we observed that normally distances covered were exceeding the 100, 120 kilometers. That is normally the standard distance for AC, for HVAC interconnection technologies. And so for this reason, we, let's say, the HVDC was the standard transmission technology used to expand the system.
Maybe to mention as well, we use this standard size of 2 gigawatt, which is about to develop. And we use this over the entire time horizon. And we are happy that this is an iterated exercise every 2 years. So whatever development in technology or prices will happen, we can consider then this in subsequent editions.
Yeah.
Mm-hmm.
Thanks to you both. Yeah. Moving to the next question from Abby. What do you mean when you say that generation assets are out of scope?
Yeah, this is also.
No,
this is in the cost and benefit. So of course we do model the offshore res and their behavior based on wind timelines. But when we assess the cost and benefit, we don't count the cost for generation assets in these considerations. But of course, in the modeling, everything is in.
Yeah, and by the way, you also find Rodrigo put the written answer there. So we are not expanded generation, but of course, as Anke said, we are modeling it because our models take into account the different the patterns that characterize the capacities overall in the different European basins.
Next one by Alex. How do you think the 8% arbitrary demand increase can be improved in future iterations?
Oh, that's part of the scenario exercise, actually,
Yeah.
because in scenario, the tool can invest. So first we start with the national trends, and then we have trajectories on everything, and then the optimizer can invest in generation, in flexibility, in demand side response, whatever, and so this is then part of the holistic approach that also the demand will end up somewhere. According to input from TSOs, input from stakeholders, and then that's modeled as part of the scenario process. When we come to the TYNDP, it's 26, yeah, we have a holistic exercise. This time we had to split a bit in slices, and in the offshore slice of the TYNDP 24, this is one of the simplifications.
Yeah, it's basically for the same reason that we use the TYNDP 2022 models. There was, let's say, for this first edition, a problem in aligning all the timings of all the different products. And since the scenarios 24, back when during step 1 of the ONDP was still in the process, we had to assess the information available at the time and identify let's say, reasonable amount in increase. Because again, the increase in electrification is confirmed. The question was, all right, how much? In the future editions, that won't be a problem, because again, aligning the timeline of development of all products, then the demand will be assessed, let's say once and for all in terms when you set up the reference scenario. And I think it can also, I mean, the linear programming question here, the high-level nature of the ONDP required a type of investigation that started from scratches, because right now we have, let's say, received by the member states the targets and simply the aggregated targets, but we had to understand how the, let's say, the optimal amount of capacity to interconnect through hybrid infrastructure. And linear programming was, first of all, better suited to understand, starting from, let's say, this blank page situation, the increase in capacity needed. And so also fitting the fact that we were not looking for single projects. We were more looking at, let's say, more strategic view of the capacity connecting the nodes.
But you can look forward to TYNDP 26 when we will have a joint exercise, a holistic optimization of offshore and onshore systems. So then we will have the joint optimized expansion of offshore and national grids.
We are running a little behind schedule, so I would take one more question on ONDPs. And the next question is, if you can scroll back up, maybe. How does the modeling as part of energy planning then interact with MSPs?
MSP is input.
Yeah.
Yeah, and interaction would be that, yeah, then the MSPs would be changed. But this is then subject to member states negotiations and member states activities, because it's the member states, national governments who are responsible for what happens actually offshore. Optimally, they collaborate. They do collaborate already in North Sea and Baltic Sea. I don't know so much about the more southern sea basins, but we use what is available, and what is available is mostly to the closer to now time horizons. The further we come into the future, less information is there, because that's a highly complex topic. So we used experience from how we know what is the comparison of bird's view and actually line lengths. And so we used an average value to represent properly how long the routes for infrastructure will be.
Okay, let's take one last one. How do we decide the location of offshore wind generation corresponding to national objectives?
That's that is an input that we gather from the national level information, either from member states or from the TSOs. We do not reassess, let's say, in the UNDP, the location. In the data gathering phase, our members deliver the data in coordination with the studies performed at national level or any other additional data available in their country. So the UNDP is not, let's say, rediscussing location. That is a direct input coming from the different members and member states.
Thank you very much. So we have to move on to the next presentation. There are some questions that were not answered, so we will answer in writing and publish everything online. So everyone is going to get an answer. So now I will ask the next two speakers to join us. So it is Louise and Simon from RTE. And as said, if one of you could share the screen so you can pass your own slides.
Yes, I'm going to share the screen. Okay, you should be able to see it normally. So hello, everyone. I'm Simon Bouchiou from RTE, and I'm going to present to you the methodology for the system needs study. So basically, this is a study that already exists, but we'll show you, we'll talk about the existing methodology and the updates from the TYNDP 2022. And Louise, also from RTE, will be presenting this with me. So first, general background. What is the goal of the study? What do we do in this? So the identification of system needs. The goal of the study is to assess which increase of cross-border capacity or flexibility capacity or anything else, but basically these two can be valuable and how it can help to reach climate agendas of European countries, how it can help to keep security of supply under control, and also to reduce costs of production throughout all of Europe. So it's a global optimization of what are the needs in terms of cross-border capacities and flexibilities that can help basically the European electric system to be more efficient in different ways. So this is a study that already exists. So I'll just show you some example of results that we have from the previous TYNDP, which from the previous AOSN, which was made during the TYNDP 2022. So as I said, the goal is to assess what are the needs of the system. So basically the result is we say what are the needs for the system. So in the TYNDP 2022, the study was made for 2040, for 2030 also, but the result for 2040 was that there is an interest in developing 88 gigawatts of additional cross-border capacities. This is between 2025 and 2040. So this gives us kind of a roadmap to what we need to do in terms of additional cross-border capacity to reach the optimal electric system. There was 88 gigawatts of cross-border capacity, 41 gigawatts of storage, and 3 gigawatts of CO2-free peaking units. So new peaking units to help the system be more efficient. So obviously these new cross-border capacities and flexibilities have costs, which was around 6 billion euros per year. But in the other hand, it helps the system be more efficient, be more cost efficient. So it would reduce the production costs, so increasing the SU basically, the socio-economic welfare by 9 billion euros, which is inducing all in all a benefit of about 3 billion euros per year. So the TYNDP 2022, we said that between 2025 and 2040, there was an interest in developing 80 gigawatts of cross-border capacity, 41 gigawatts of storage, and 3 gigawatts of CO2-free peaking units. And the goal of these new cross-border capacities and flexibilities would be to have a benefit of 3 billion euros per year. But so obviously the one of the main results is the cost of the electric system, which is reduced. So this is what we show here, that on the left we have the starting point, we have what happens if we do nothing in terms of new cross-border and flexibilities, cross-border capacities and flexibilities. And on the right, you have the optimal system. So the first thing is obviously about costs, because the main impact of developing this is reducing the costs. So as I said, around 3 billion euros per year. But we also assess some other benefits. Because the optimization of the whole of European production plan is not the only thing. We also show that these new flexibilities and cross-border capacities can ensure security of supply throughout all of Europe. So we reduce the risk of a global blackout. We also improve the renewable integration by 42 terawatt-hour per year. So this is obviously needed for the Europe to reach its climate agenda. And the consequence of this is that we reduce, because integrating renewables will be used to reduce gas-based generation by 75 terawatt-hours. So this is basically reducing CO2 emitting generation. So this can be said in terms of CO2. In total, the optimal portfolio that was found in the TYNDP 2022 allows for a reduction of 31 megatons of CO2 per year if we develop the optimal electric system between 2025 and 2040. So now, how do we reach these results? How do we find these results? So this is very high level slide to show the global philosophy of the study. Basically, the first step is to identify the economically viable interconnectors and flexibilities without a set scenario. So this is what I showed you before. It's the first step is to find where new cross-border capacities and flexibilities are valued. Then this shows that there is already there is at least one more beneficial configuration. So that means that even if the results are given in terms of cross-border capacities and flexibilities, other technologies can also be valuable in a given area. So a cross-border capacity is not necessarily an interconnector. The goal is to try to push TSOs and project promoters to find new solutions, because we assess the needs, but we do not really give the solutions. So in the end, the goal is that TSOs and project promoters can explore different solutions. So some solutions are given on the slide. So the goal is that TSOs and project promoters can explore different solutions to satisfy these needs, and it could be interconnectors, storage, and peaking units, but it could also be other things. So for example, we put here smart grid or power to gas. Those are things that are not given to the optimizer, but having the results that there is a need in cross-border capacity or in flexibility in a given area, project promoters could think of developing such a project in this area. While the IOSN we try to identify the needs. To do this, even if we want to address the needs and not the solutions, we have to try the solutions in the models. So the solutions that we're testing, as I said, are cross-border capacities. So basically, these are grid reinforcements and flexibility reinforcements that are storage and picking units. So we will discuss it a bit more detailed. It will be detailed later. But the goal is also to have all of these solutions optimized together. So this is the goal of a co-optimization, because we want to have insights about the mutual influences, such as competition, or in the other hand, synergies that can be existent between some investment candidates. So, for example, an interconnection can be valued if there is some storage in the area. So this is why we want to have both interconnectors and flexibility optimized, or yes, optimized together to have a optimization and have all of the mutual influences in the scope of the study. So this slide shows very high level too, but shows the main steps of the study. So we have 3 main steps. The first step is setting what we call the starting point. So the starting point is made of 3 things. There is a starting grid. So obviously, if we want to invest in interconnections, we have to have a starting grid to know what we're investing on. So we have a starting grid. We have a scenario also, because we are based on the scenarios of the TYNDP. So for the IUSN of TYNDP 2024, we are planning to have 2030 on national trends, 2040 on national trends also, and 2050 on distributed energy. So we can have different scenarios on all different horizons. And the third thing about the starting point is the investment candidates. So the investment candidates are interconnectors and the flexibilities that are not in the grid of the starting model, but they can be added during the optimization phase. So it's what we propose to increase as cross-border capacities and flexibilities. And again, we will have a bit more detailed version of it in the next slides. So the optimization phase is the second phase. So here the goal is to choose in the candidates given, we've given in the starting point. The goal is that the optimizer will choose the ones that will get to the system to its optimum, meaning the optimum is the minimization of the operational costs, which are the costs of the system, and the capex that will be the cost of our investment candidates. So basically, the optimization phase is the phase where we find the most cost-efficient system for the most cost-efficient grid and the flexibilities for the system. And once we have finalized this optimization, we have the optimal power system. And with the starting point and optimal power system simulations, we can address some of the topics that I talked about earlier. So we can have how much renewable was integrated, how it lowered the costs, how it helped for security of supply, and so on. Just a quick presentation of how we assess of what's between the optimization phase. So basically, we are investing. We are investing in cross-border capacities and flexibilities. So as you invest, you increase your capex, but you also make your electric system more cost efficient. So that means that you reduce your OPEX. Those are the two graphs on the left. And the goal is to minimize the sum of the two. So if you invest nothing, you have no capex but very high OPEX, because your system is very not optimized. But if you invest an infinite amount of money, you reach a low limit on the system's operational costs, but your investment costs will keep on getting higher. So your capex will be infinite. Between these two very high solutions, there is an optimum, which is found by the optimizer. And the optimizer, historically, it was a module of ENTSO-E because all of the IOSNs were made on ENTSO-E. Now it will also be done on Plexos for 2030 and 2050. Now I'm going to let Louise present the part about more about the grid assumptions.
Yeah, hello everyone. So I'm Louise Ansart. I will here in this slide explain the difference between two models that we use in IOSN. So the NTC model versus zonal model. So in the two models, we will it's a way to represent network. In the two models, we begin with a market study. In this market study, there is nodes and links. Nodes are considered as copper plates in that kind of model. And then you've got links with a capacity link in each link. You can set the capacity as infinite value, or you can limit it with the limit you choose. So you also have what we call binding constraints, the third column in the table. Binding constraint, it's used to add some model constraints in the optimization. For example, in zonal model, we want to model the behavior of physical network, electric network, and so we need to add binding constraints to make Kirchhoff's mesh rules. So as you can see in the table in the top of the slide, there is first the NTC model. We've got one node per country, or I will say maybe per bidding zone, and you've got the link between each bidding zones. It's cross-border links, and we limit the links between cross-borders with their capacities, so NTC capacities. There is no other bidding constraints in the market simulation, and so it simulates a network as copper plates connected by HVDCs nearly. Then you've got the zonal model in the bottom of the table. There are more nodes per bidding zone. So we split a bidding zone in several nodes, and we add Kirchhoff's mesh rules. We also have the links between bidding zones and links between internal zones. So in last exercise, we only, I will precise it in the next slide, but in the previous exercise, we only add limits on cross-border links. So the zonal model aimed to simulate a network as copper plates, but connected by AC grid. And so it's closer to the real network. And so you can see also the example below. So to see what is really the difference between the two models, there is a small example. Let's assume that we've got 4 nodes, A, B, C, D. You've got free production in A node, and you've got load in D node. If you've got NTC model with a capacity of 1 gigawatt between each zone, you can use as HVDCs your links, and so you've got 1 gigawatt on each links, and you can provide the load from D node with all the wind in A node. But if you've got a zonal model with, in this example, all the impedances are equal, you will have more flow in the direct link between A and D, and it will be more than the capacity because it will 1.5 gigawatts on these links. And the optimizer will not allow to let 1.5 gigawatt on this capacity if we limit it, because it's if it's a cross-border capacity. And so it will need to use the other generation in B or C node, for example, to respect all the constraints. And I will maybe go further in the further slide, because I want to precise on I want to precise on what we will have to add in this exercise compared to TYNDP 2022. So we plan to with the null model, we've got also internal links between several zones in one bidding zones. In previous exercise, we didn't activate the limits of this link, but we plan to do a variant with this in this exercise with internal links limited between zones in a same bidding zone. The results of this variant will be compared to the one without internal links limited. I just want to precise that we will not have internal candidates in the exercise. We will only evaluate cross-border candidates, but the limits in internal links could change the final results. Then how we build the zonal model. So we need two inputs, the generation and load database, so the PMMDB at the time horizon. We also need a grid model, a detailed grid model, merged from all the countries of ENTSO-E zone. So at the beginning, we still have a classical market study, NTC study, without any mesh rules, and because we will implement it at the end for the zonal market study. From this classical market study, we will with the load flow calculation, we will calculate a sample of synchronous flows on the detailed grid, and with these flows, we can assess equivalent impedances and zero balance flow corrections and equivalent capacity to build a zonal market study. The zonal market study will be we'll have different zones in a bidding zones. It's the splitting of the bidding zones were already done in a clustering exercise, where generation and load assumptions were splitted also in that zonal level according to the clustering of the bidding zones. And of course, we add the implementation of controllable devices, so PST and HVDC in the zonal market study, because we've got more details and it's possible to use the real physical behavior of these controllable devices. So finally, I just wanted to precise that we will not change the clustering that we made in last exercise. We do not expect to change it because it was a huge work in last exercise, and it was already made to improve quality of the model with the new clustering. And this new clustering nearly respects the electrical behavior of all the zones. And we do not expect major updates in TYNDP 2024 exercise. I think, Simon, you've got your mic up.
Yeah, Simon, we cannot hear you. At least I cannot hear you. Oh, no, it works.
Okay, it should be okay now.
Yes.
Sorry, it was very. Okay, so some things about the investment candidates. Just first, a quick. So Louise talked about the two different models that are possible, that are ENTSO-E and zonal. So here on the left of the table, you have the three horizons that are planned for the TYNDP 24 IUSN. So there is 2030, 40, and 2050, as I said. 2030 will be in ENTSO-E, and 2040 and 2050 will be in zonal configuration. So we will have both ENTSO-E and zonal models, but on different time horizon. There will not be a single time horizons with two studies, both ENTSO-E and zonal. So here we want to present what are the investment candidates that are to be included in the study. So first, in TYNDP 2022, to remind a bit, the candidates were interconnection only for 2030, and it was also for 2040. But flexibility and peaking units were already studied, but only on the 2040 time horizon. So in 2030 there was only interconnection, and in 2040 there was interconnection and storage and peaking capacities. So here the goal, so the study of these three types of candidates was quite successful in the 2040 horizon. So here the goal is to include them in every time horizon. So both 2030, 2040, and 2050 will have these types of candidates. And an improvement from TYNDP 2022 is that for 2040 and 2050, we plan to have hybrid offshore candidates, as Antje and Francesco quickly talked about. We will take the ONDP outputs to make it into candidates to assess them with the onshore optimization, to have both an offshore and onshore optimization. So this is the candidates that we plan to have. And for the starting point, we have to choose a starting point for every type of flexibility. So for interconnectors, the starting point will be 2030 grid. So that means that for the IUSN 2030, the goal is to see how we can go beyond the interconnections that we already have. It will be the same for storage and peaking. But for 2040, it means that we take the starting point of 2030 and we see what can be added to have an optimized system. For storage flexibility and peaking flexibility, the goal is to be coherent with the interconnectors. So it's also based on the 2030 level. So it's based on the PMDB of National Trends 2030. And for the hybrid offshore, it's not yet settled. It's still under discussion. So as I said, one of the main differences between the TYNDP 2022 and 2024 was that we are planning to have a new type of candidates that is the offshore hybrid investment candidates. So there was a presentation about the ONDP earlier. So the ONDP identifies corridors. This is what we call, from the IOSN point of view, the outputs of the ONDPs. The goal is to see if these corridors are valued in the optimal electric system when they are in competition with onshore interconnections and flexibility. So to assess this, we take these corridors and we translate them into ONDP investment candidates. So this is offshore hybrid investment candidates. So the methodology is basically the same as the ONDP. We do not take the generation into the cost benefit, only the cross-border capacity part. But the goal is to see if this has an interest when compared to other investment candidates. And there is a conceptual that will be explained later, because we have real and conceptual candidates. This one I taken as conceptual. Now, if we study this type of candidate in the IOSN, we might we hope to find some as valuable for the optimal electric system. So these are the one that will be identified as needs, and the ultimate goal is to, so as I said a bit in the beginning, is that these needs identified may become real projects. So the goal of the study is to help TSOs and project promoters to evolve these corridors into real projects for the next TYNDPs that could be studied in the cost benefit analysis in the CBA part of the next TYNDPs. Now a quick presentation of how we do the optimization. So we need to have 2 loops of optimization. So this is something that was already done in the previous IOSN. It was already the case in the TYNDP 2022. But 2 phases are needed to run the optimization because we have, due to the complexity of the models. So we have to have different candidates into the different loops. So the first loop of optimization has what we call the real candidates that are existing interconnection candidates. So this one we have been collected them. We have collected them earlier this year. They've been collected from TSOs earlier this year. And for the flexibilities candidates, so for storage and peaking unit candidates, the goal is to take it from scenarios, so for the PMDB. So basically, the starting point is 2030. The real candidates for storage and peaking flexibilities are what is increased between 2030 and 2040 in national trends for the 2040 real candidates. In the second loop of optimization, we have much more candidates, but conceptual ones. So these gather interconnection candidates. So these are also been collected by TSOs, but as they are not real candidates, it's more standardized. It's more TSOs chose to give standard interconnection candidates, which are not existing as projects, but it's to see if there is a need. We put projects about everywhere we can. We also have conceptual flexibility candidates. So here it's for every zone. We give candidates for flexibilities. We we have standard costs, and we give candidates for every zone. So every zone can add storage and picking unit capacity. And for the, as I said before, for the offshore, we have the ONDP conceptual candidates, which are derived from the ONDP corridors. These candidates are given in the second loop of the optimization. And so the goal of all this is to have these two loops of optimization, and then we have all of the needs. So we see which candidates have been chosen by the two loops of optimization, and we have the needs of for our scenario. So basically, this has not changed. The only thing that has changed from TYNDP 2022 is the add of the ONDP conceptual candidates. But all of the rest is the same as the previous TYNDP. Another thing that is not, at least not planned to change for this exercise is the climatic years. So we plan to have 10 climatic years for 2030 and 3 for 2040 and 2050. In the TYNDP 2022, it was 3 climatic years for 2030 and 10 for 2040, but we do not choose climatic years based on the horizon, but based on the complexity of the model. And here the thing is that for zonal models, which are very, very heavy, we cannot take more than 3 climatic years. So all of the zonal models will be with 3 climatic years, and the 2030 NTC will be with 10. The goal to have more climatic years is to have more different situations assessed, and this is really needed to have a solid study about the security of supply. So security of supply is way better when it's on 10 climatic years than 3. So these are the main features of the methodology, and to put that in front of what was asked and what was said by the stakeholders, and from the TYNDP from the IOSN of TYNDP 2022. There were some main subjects that were raised by the stakeholders. The first one was that 2030 was too close to initiate any project, so it couldn't be the main horizon, and also that 2050 should be included. So this has been done with 2050 because we will study 2050 with distributed energy. We will still keep 2030 and 2040, but this time the priority will be given to 2040 and not 2030, because indeed the goal of the system needs is to see what is needed, but we need to have some time to address these needs, and so 2040 is more relevant than 2030. On scenarios, last TYNDP, the only scenario studied was national trends. So it was asked to assess the needs in a bit more ambitious scenarios and have not only have one of them. So even if in this exercise we do not plan to have the 2 scenarios on one time horizon, we want to have different scenarios. So this is why we will study distributed energy in 2050, even if we keep national trends for 2030 and 40. And for the ambition of the scenarios, national trends this time will be more ambitious than in last cycle, so it will be more representative of an ambitious scenario. About the study of the study's role in the TYNDP process, in the global TYNDP process, because it's a bit hard to know which part goes where, and the interrelation with other parts of the TYNDP. So this is one of the points of today's seminar, mainly to show what gives the system needs in the global TYNDP, but also what are the things that we do in common with the ONDPs. Also for investment candidates, so in the TYNDP 2022, it was the first time storage and peaking flexibilities were studied, and it was quite appreciated. So this is why we decided to study this again, and this time on all time horizons. So not only in NTC but also in zonal models, and this is also why we want to address offshore needs, which was another demand from the stakeholders to have the offshore needs more addressed in the study. So this is why we wanted to add the ONDP output to study offshore and onshore needs. So we wanted to have some offshore candidates in the optimization. So I think this is about it for the IOSN methodology. Now, if you have questions, I'm sure you have, I'll be happy to answer it.
Thank you very much, Louise and Simon. So before we start a short Q&A, we have a quick poll for you. So still on Slido at the same link, same code. You can see already, I see that 12 attendees have already answered. So you can go to Slido. In the meantime, maybe I will read out loud one of the questions we have already. One question from James is, how are the subzones established? So I mean, this is probably about the zonal model. How was the zonal model developed? I don't know if it's more for you, Simon, or for Louise.
Yeah, so it will be described in the methodology report. I think it was already in the last one also, because the methodology will not change, and it's the clustering of the last exercise. Just to quickly answer, it's the split of subzones is made to respect electrical behavior of each zones in the network. And it also highlights the weaknesses of internal networks. So the weak links that could limit cross-border capacities for exchanges in the market will be a link between two subzones.
Thank you. Now going back to the poll, I see 23 answers and growing. Okay, I see the first, the highest rank improvement so far is to consider additional technology type in investment candidates shortly before the assessment of the 2050 and the identification of the offshore needs. That's the trio on top, and two other options we had. Of course, there could be other improvements, and then we'd love to hear from you. Two other options we had in the poll was to assess additional climate years and to further develop stakeholder engagement and transparency. Now maybe I see some people are still answering, but I would still move to the next question in the interest of time. So how are the results of the IOSN, so the system needs study, considered for the TYNDP transmission projects cost-benefit analysis? Maybe actually I can help answering that one as a start and someone can complete. So the system needs study and the cost-benefit analysis of projects are two separate processes. What we do is that we ask promoters to consider the results of the system needs, so on the borders where their projects are located, and to tell us whether and how their project can help to address one of the needs that has been identified by the study. Maybe one of the two of you or someone else among my colleagues want to complete. Otherwise, I will move to the next question from James. Is the use of historic climate years still relevant given the rate of change of the climate? Simon?
Yeah, I think that the climate years used are based on the historic, but are also take into account the evolution of climate. So we have different climate bases for different horizons, and for 2040 we have climate years that correspond to 2040 climates.
Thanks. And the next one, it was said that national trends is more ambitious now. Can you explain how? Okay, it's more a question about scenarios. Has the national energy and climate plans from this summer been included? Yeah, it's more a question about our scenarios colleagues. Maybe if Rodrigo is in the call and he wants to answer that one. Yeah.
I can take this one, yes. So looking at the scenario building in previous cycles, it was to some extent, let's say, a simple amalgamation of the national energy and climate plans, which would not necessarily lead to meeting the European targets. In this cycle, even though we still start as the amalgamation of the NECPs, we have explicitly the target of meeting the European binding targets. So in that sense, the national trends will ensure that the 2030 European targets are met in the development of the scenario. So it is in this sense that the NT is more ambitious this cycle compared to previous cycles.
Thanks, Rodrigo. Next question. System needs, of course, are important, but increases DER. Not quite sure what DER is. DER integration with DSO grid and use of the high flexibility possibilities and synergy with local opportunities have really high influence on the whole system. So I guess the question is, how is DER integration with the DSO grid considered? But I'm not sure I understand the question.
I'm not sure either about what is DER, but I think if it's something about the DSO grid, the study should not be. I don't think that it addresses this, because while we try to use a zonal model to be more precise, it's still quite large zones, and it's only representing the transport system and not the distribution.
I see that Andrew wants to intervene.
Yes, I think I answered this question within the written section. So I think the system needs studies are focusing on TSO voltage level and on transmission infrastructure and flexibilities. However, I understood DER is dedicated to RES. They are well investigated within scenario building process, and the outcomes of such a process are inputs for the IOSN study, and for 2050 DE, this is already in inputs. On the other side, I understood from the questions that were raised was the flexibility input from DSO level that was asked, how do we investigate this? And here the answer was that the needs that are identified within this system needs study could be addressed on different levels, and different technologies can be used to address such needs. So we are not disregarding any investments on DSO level. We are identifying the needs, which are mainly market-based, so they are most cost-effective, and the solutions that can address these needs could be investigated also on DSO level. So these are not disregarded by ENTSO-E by any means.
Thanks, Andrew. We are again a bit pressed by time, so I will take one last question. Yes. If you can scroll up. Yeah. Does it mean that the results of the first loop will be the starting point for the second loop, Simon?
Yes, it means that we do the first loop, we have identified candidates that are given by the optimizer. This one will be in the start of the second loop. And another thing that I didn't detail, but the candidates that have not been chosen by the optimizer are given again as candidates in the second phase. So basically, real projects, if they are taken by the optimizer, they are given in the starting point of the second loop, and if they are not, they are given again as candidates in the second loop.
Thank you. So like for the questions on the ONDP, which we could not answer, we will also answer in writing to everyone. So it will be published online in the few coming days. Now I would like to give the floor to the last presentation of today. So Joao, I see you are connected. Yes. Hi, Joao. So you have the floor.
Yes, thank you very much, Leah. Project Inertia is a cross-committee project with experts from 3 committees: system development, system operation, and also the committee from research and development. To support us, we have also here today Francesco with support from the Secretariat. And the goal for today is to show a main part of what are the results we have so far and how the TYNDP investigation of system needs can, in a final stage, support the implementation of the conclusions. ENTSO-E has published already a report on the aspect of system splits in continental Europe, and the Project Inertia Phase 2 is a continuation of this work. And now with a goal to update all the results and finally take conclusions on what is the intended level of resilience that we want for the system. For this is a technical question, but goes beyond technical in some respects. The project also has the goal to have a strong engagement internally and externally to present the conclusions and also to have a debate on the findings and finally on the criteria to define system resilience against system splits. The analysis of the project is supported on the TYNDP scenarios and TYNDP available data. So here we are looking at the market nodes of the scenarios and then assessing all the possible combinations of system split cases that we can have for continental Europe synchronous area. And then for all these combinations, we will assess one important element, one important indicator, which is the ROCOF. And for each of the scenarios, for all the hours of each scenario, and for all the system split combinations that we are considering for the system, we will assess if the 2 subsystems that we can have in a system split will be able to cope with this indicator, the ROCOF. And if it is below 1 Hertz per second, it is considered manageable. It is above 1 Hertz per second, it will be considered critical and might lead to consequences such as a blackout. In order to identify the most severe cases, we are also specifically looking for the cases where we could have these non-manageable ROCOFs appearing in both subsystems after a system split. For this, we call it the global severe splits, which are the cases that we consider the most severe, the most relevant to analyze, because in case of restoration, we will not have a safe system to help bring out the other. This does not mean that any subsystem that might go to blackout, it's not severe, it's not important, but just for the analysis that we are taking in this report, in this project, we are looking at most severe cases. To give you an idea of the overall results using this analysis of the ROCOF, so that you can quickly understand the plots, you have for the different TYNDP scenarios of 2022, from National Trends 2030 up to Global Action 2040 and Distributed Energy 2040, all the ROC-off that appears in all of the subsystems that are split for all the hours of the year, for all the scenarios, for all the split combinations. All the dots represent the ROC-off in the subsystem split. And here you have the gray dots, which are the cases where only one of the subsystems experienced a split exceeding 1 S per second ROC-off. And the blue dots are the cases where both subsystems experienced both 1 Hertz per second ROC-off. And you can see that the trend is very clear. You can also have from this analysis the scale and the range of the challenge. You see that when we move from the 2030 to 2040 scenarios, we have more critical cases. And also when we look at the cases that could trigger global severe cases, it's also clear that the situation is getting more and more difficult to withstand. So the results from our previous analysis are fully confirmed with the updated scenarios. And we also see that from here, we have a progressive decline in system resilience in what concerns system splits. So some actions need to be considered. And from the project, we consider that the way to tackle the ROC-off challenge is to put in place what we call foundational measures. And those foundational measures should be in the system all the time before the system split happens, because this is what helps the system to withstand the problem, to be able to have lower ROC-offs. And all the enhancement of the dynamic behavior will need to come on top of that. And so the distinction is made in this way. In what regards the identification of the needs, we present here a study case to show how this can be made. The criteria used for this study case is to eliminate all global severe splits for 2030 national trend scenario. And on this plot on your left-hand side, you can see the amount of kinetic energy that would be required to have a cover of all the global severe cases. And you see on here, on the maximum level, it will be the necessary kinetic energy to clear all cases. But if your criteria is different, if you'll be allowing a system resilience to be lower than this, of course, the amount of kinetic energy necessary would be lower. So this illustrates that we need to agree on the intended level of system resilience, and from there we'll be able to define the needs. One important note to take into account is that even if you would clear all global severe splits, all these gray dots remain in the picture. This means that also severe splits will be possible. This project will go for a minimum level of kinetic energy to build. This does not exclude that some regions might take the decision to go beyond the analysis to cover the most critical scenarios. As mentioned before, we have divided for organization the solution measures into foundational measures and enhanced response measures. So the foundational measures will define the minimum level of resilience that is intended for the system. So this means keeping inertia above a certain level so that the initial ROC-offs in the center of inertia will be limited. The enhanced response measures, they will build on the foundations. So they are the withstand capability of the users, for instance, generators, and also all the frequency containment support capabilities that will limit the amplitude of the frequency deviation. For completeness of the analysis, we also mentioned as last resort measures, restrictions to market. If we imagine that the initial ROC-off will depend on the imbalance and on available inertia, you could consider, at least theoretically, that you could impose must-run units or some sort of exchange limitation of power. But last resort measure here for completeness. In what regard the foundational measures, we have available technologies, very established synchronous condensers with flywheel, new technologies for STATCOMs with grid forming capability and inertial response, and also power park modules with grid forming capability and inertial response. All will be necessary. Important to note that in the short term, installation of synchronous condensers and StatComs will be readily available. And we not say in the future, we say as soon as possible, deploy Power Park module with grid forming capability and storage. And why this sense of urgency for Power Park modules? RFC 2.0 is introducing very important requirements in what regards this capability, but we need to remember that until the implementation, until full force of RFC, many more megawatts of generation will enter the system without this capability. So they are needed as soon as possible, and when they start to enter, still they will need time to have a number that really supports the system. And so this links to the initial question that was here on the webinar. This project is about creating the conditions to make the power system compatible with the energy transition targets. Finally, Project Inertia Phase 2 is ongoing. The next step is toward assessing the intended level of system resilience that is required for the system. And based on the final conclusions, the TYNDP investigation of system needs can support this assessment and present the overall inertia needs. Just to finish, what are the principles that the project is following? We consider this a step-by-step and pursuing non-regret and adaptable solutions. For this, global series splits as the most relevant of the issues are used as criteria for recovering the system resilience. And we also say that it's about recovering. It's not about creating more resilience that we have. We are losing the resilience. The question is, how much of this resilience are we willing to lose, and how much do we want to recover it back? In order to be adaptable and non-regret, TYNDP scenarios for selecting the minimum level of resilience will be 2030 national trends or an equivalent type scenario. This means the less ambitious, the closest one. And from there, you can meet the required level of inertia. It's also understanding that countries should select the best combination of foundational measures, and taking opportunity of the TYNDP regularly assessments. It can be reassessed every 2 years. We will have a dedicated workshop during November, and so everyone will be invited to, if interested, to see a longer presentation with all the details of the study. Thank you.
Well, we are arriving to the final part of our webinar today. We had around 25 questions, very interesting regarding inputs, methodological aspects, comparison with other international approaches. So thank you very much for the interactions. Thank you also to the presenters that have been explaining the different parts of this exercise. And as next step, please don't forget the possibility to interact. You can provide your input until the end of November on the methodology. Here you have the email address to send your comments. Remind also that you can join the webinar on the inertia study in November, as you all have just reminded. Be aware on the 24th of January next year for getting the ONDPs per sea basin, and please participate in the public consultation on those reports, because every improvement will be very useful for the 2026 exercise. And remind that also in summer 2024 we will publish the results of the system needs study, and it will have a dedicated public consultation. So that's all from our part. Thank you very much, and you have also on the website the whole presentation recorded to contact it and check after today. Thanks.
Sorry, so I was saying, I think I was muted. We will publish the slides and the recording this week still, and we will also answer in writing to all the questions we did not have time to address. Thank you very much, and speak to you soon.